All right, in this video, I want to teach a bit about the relationship between the graph of a function f and the graph of its derivative f prime. So here I have a picture. This is a graph of a function. We don't know what its algebraic description is, or if it even has one. We don't know much about the exact coordinates of these points. We could estimate them from the graph, but we don't really need to know all that. What we want to do is just take this graph and see if we can use it to roughly sketch the graph of f prime. Okay, so how can we begin? Well, one useful thing to look for is horizontal tangent lines, because horizontal tangent lines are going to have a slope of 0, which means that the output of the derivative is going to be 0, which gives you a point on the x-axis, an x-intercept. So let's look for points where we're going to have horizontal tangent lines. Well, over here, here's a portion of the graph where the tangent line would be horizontal for any point on this part of the graph right here. Okay, this is a flat portion of the graph. The slope of the tangent lines at all the points on that flat portion are all 0. It's kind of like a constant part. And as we and as you will learn soon, the derivative of a constant is 0. So for drawing the derivative, I'm going to start here with an open circle, go all the way to here with an open circle. So those x coordinates line up with the beginning and end of that flat segment. And this, I'm just going to go ahead and go like that. So my derivative, which is going to be in blue for this video, derivative, which is going to be in blue for this video, it is going to be a horizontal line along the x-axis, like 0 function for that portion of the graph. Okay. Now I did open circles at the endpoints because, as I talked about with differentiability, when you have a sharp corner like this, right, those points there, it's not differentiable at either of those 2 points. So we have undefined derivative. Now what's going on over here, we have tangent lines that have this slope. Now what is that slope? If I go down by some amount, let's just do it with like that. If I go down by some amount, how much do I go over? This looks to be approximately like down one unit, down 1. And then to the right by 1 unit. So this slope should be -1, right? So that means that what I want to do is find -1 on my y-axis. And for that portion of the graph of the derivative, it's going to be, again, constant down here at -1, like that. Now you notice it jumps, right? Jump in the derivative graph, because here, it's 0, and then here suddenly it's -1, and that's a sudden jump in the slope. This point here where it's not differentiable corresponds to a discontinuity in the derivative f prime. This is blue graph here. Remind you, it's going to be the graph of f prime. Okay, so now what's happening over here? I mentioned it's good to start with places where the tangent line would be 0, would be horizontal. Let's get back to that idea. We had this area where it's horizontal. Another place where you're going to have a horizontal tangent line is at like the top of a hill, like this. There we have a horizontal tangent line. So that x value, whatever that is, we're going to have an x-intercept. So that's going to be a point where the blue graph, there we go, is going to have an x-intercept, because the output is the slope of the tangent line, and the slope of the tangent line is 0. There's another point like that over here. I said the top of a hill, but also the bottom of a valley. This is another point on the original graph where the slope is 0. So our derivative graph is going to be like this. Now, in general, in between these 2 points, we have positive slope, right? It's not constant, not a straight line. but we're going to have some positive slopes along there, right? So we should expect our blue graph to be above the x-axis somewhere, somehow above the x-axis here, positive, because the slope's positive. However, over here, we see negative slopes. So we're going to expect our blue graph to be below the x-axis somewhere down here, maybe. Okay. Remember, the slope value is going to be the output of the derivative, and therefore the y-coordinate values. So one thing we can do is look for the maximum slope that we reach on any given segment. So let's focus on this segment that's in between those two horizontal lines. I would say the point on the graph where it appears to have the steepest slope is going to be about here. Steepest. And I'm going to estimate the tangent line. About that, right? And we can guess what that slope is. I'm going to guess that slope there is approximately 1, positive 1. Okay, so what that would mean is that at that x value, okay, trace that x value down to the x-axis, that x value right there, at that x value, the derivative is going to output 1, which would be right here. Now, this is just a rough sketch. So I just want to basically connect these dots, that dot, that dot, and that dot, with a curve that makes it doesn't go higher than this right here. So something sort of like that. Pretty good. That'll do. Okay. So now let's focus on the bit outside of that little segment. Like over here, it's going to be negative. You see, this is again negative slope because it's going down. So we can expect our graph to go down a little bit. I don't know how steep steep that actually is. Not terribly steep. So sort of like that maybe. And then it ends with an open circle. And there's another jump right here. That jump again corresponding to a little corner that we have. Sudden change in slopes. Over here, it's negative, so we're beneath the x-axis. And I don't know how steep. This is getting pretty darn steep over here. Let's see. I would say at this endpoint. And that slope, I'm going to guess, is approximately -2, about down 2 over 1, or down 1 over a half. I'm being very rough in my approximations here. So let's guess that this comes down here and comes down to somewhere about there. And then, or rather, something like that. And that's pretty much it. There we go. We've done the whole thing. So this is the graph of f prime to the best of our ability. Okay. And this demonstrates connections between the function f and the function f prime. You've seen that when f of x is horizontal, f prime is equal to 0. When f of x is decreasing, f prime is negative, like there. Over here, it's negative. When f of x is increasing, f prime is positive. And when f of x has like a maximum, I said maximum, but a maximum or a minimum point, at least in these instances, f prime has an x-intercept. That's not a universal rule, as we will learn when we get to chapter 4. We'll talk more about maximums and minimums then, but it is a helpful connection that often holds true. All right, so now that I've shown you this stuff, I'm going to take you over to the internet and show you a couple of things over there. So on D2L, you have in the content section links to useful stuff. And one of the things in there is the Geogebra Applets. So click on that Geogebra Applets link. I actually already had it open in the tab, so I'll close that. you have this web page. It's a very nice web page created by Mark Renault from Shippensburg University. Thank you, Mark. There's some cool stuff in here. One of these is try to graph the derivative function. This is a neat little applet that does essentially what I was just demonstrating. Wait for it to load. A bit slow. There we go. So you have this graph in black, and you have this graph in blue. So you can like grab these blue points and move them around. And the idea of this is to try to move this, this graph so that it is matching the graph of the derivative. And then we can check for accuracy, and eventually we can show and see how close we got. This is sort of a fun, fun game almost. So I'm going to look for the maximum points and minimum points. Here we have like a 0. This is where we have a maximum horizontal tangent. So we need it to cross the x-axis. It's going to go from positive because it's increasing. So I guess I'll move it up above the x-axis to negative. It's going to be negative over here. Because as you can see, the black graph is decreasing on this section here. I'm bringing these down, making them negative somehow. The next x-intercept is going to be about here. About, I guess, kind of close to 1. Let's move these like that. And then it's going to be between here and almost the end. It's going to be positive, but I do think it looks like it's going to reach 0 again, if not there, pretty close to there, maybe shortly thereafter. Just like, let's make it so that it's kind of coming down and it's going to cross over the x-axis in a moment, but it just doesn't quite get there yet. So now, so this is roughly the shape I want. It's crossing the x-axis in about the right places, here, here, and then about to do it here. Now we can check accuracy. 84%. Okay, that's pretty good. But you can kind of check to see like how negative is that really? That slope is not quite -1. I would say we're too low. We actually need to come back up and have this sort of subtle curve that doesn't quite make it to -1. And over here, the steepest point on this curve might be about here. And that's still like not quite a slope of 1. It's still less than a slope of 1. And I'm just using my intuition. I'm going to guess that it's about like that. If I check accuracy again, and now I'm 95% accurate. And if I show the result, you can see the exact curve. So you can use this applet and you can reset the graph as many times as you want, and it keeps on giving you different functions to try. All of these are smooth functions, so none of them are ever going to have like a corner, like I showed in the example. But it at least helps to build your intuition. Now, the other applet I want to show you is identify, number 12, identify the derivative function. This is kind of a similar game where we have the function over here. I guess we can kind of zoom out, look at it. Woo! Look at that function. And then we want to figure out which of these is the correct derivative. So you type 1. So you can start looking for x-intercepts. This looks like it should have horizontal tangent lines just to the left of 0. So like the brown one here has an x-intercept just to the left of 0, and so does that, and so does that, almost. So that's pretty close. But then the next one is going to be like over here at about 4. It's a little bit shy of 4. That's closer to 4. That's a little after 4. If anything, it's a little bit to the left of 4. So I might get rid of this one. That one's, I'm pretty sure that's not it. I'm going to check. Yeah, that one's not it. So yeah, so we're down to just these two. And so again, the reason I eliminated this option is because that x-intercept is the right of 4, but I think it's pretty clear that the maximum point here occurs to the left of 4. If that's not clear, let's find another way to rule this out. This maximum point where there should be an x-intercept is at about -4.5. Well, that's pretty close. Wow, these two graphs are really close to each other. I feel like that's the biggest difference, having an x-intercept to the left versus to the right. So you got to kind of estimate where that is. I think it's this one, but let's just check up here. Let's go back to this brown one. The brown one has 2 x-intercepts very close together. The second one is at about -2 and a bit. But if I go to -2 and a bit, this graph very clearly has a negative slope, not a 0 slope. So having an x-intercept there does not make any sense. This is definitely the wrong answer. So that just leaves this one. So yeah, so this is a fun sort of thing that you can do. Again, building your intuition and your understanding of the relationship between a function and the graph of its